This is the Calculus AB 2013 FRQ, question number 5. So they give us two functions. This is a non-calculator question. F and G, you should know which one's which based on your knowledge of these functions. And they want the area of R. What's nice is they've already told us that intersection point's 4 on the y-axis, and that intersection point is 2 on the x-axis. Now, if you're not sure why we know that's 2, this is different from other situations because they're specifically labeling that point 2. Now, they don't have like a line saying, okay, that's 2, but since there's no line there, they are telling you that that's intersecting at 2. Now, let me give you a different scenario. Maybe you have graph paper like this. I'm just making stuff up real quick. And you have two graphs. And it's like that. And you're saying, okay, that intersects right there. They never tell you that. That point's not labeled. That point's not given as that point. So you don't know. But this one's specifically labeled 2. And it has to be that intersection point because there's no other point that 2 could be that's given. So that's why you don't have to find intersection points on this problem. I could see why it can be confusing, but in this case, 2 is that point given, and they're telling you that. Otherwise, there'd be a dashed line, like a line where the 2 is in the 4, but there's not. So we don't have to do that part. So find the area. So to find the area, we want to add rectangles. And the rectangles are going to go this way. I mean, technically you could do rectangles the other way, but you wouldn't want to, especially down here, because that would be a nightmare. You do not want to do that. So part A, you want to add the rectangles starting at 0 and ending at 2. Again, from 0 to 2. And the height of the rectangle is g minus f. So it's going to be g minus f, and the width of the rectangle is dx. So now we're going to plug in the actual values. G, I'm going to shorthand that a little bit, minus f, and don't forget to parenthesize this. Now, I choose to split this up into two separate integrals, and here's the reason. This is a function inside my cosine function, so I need to do a u sub there. If I do u sub here, I don't want to u sub all that. That would make no sense. So I'm going to write it as two separate integrals. So I'm going to go from 0 to 2. That 4 I can pull out in front. Because this 4 is a constant, I can pull out in front, make my life easier. Cosine pi over 4x dx, and separately, I'm going to do this one here. Now the first one, I need this to be a single variable, so I'm going to call that u. And then taking the derivative of u, I'm going to get pi over 4 dx. Now I need to replace this with u, I need that to be replaced with u, and these to replace with values of u. Well, I can use du if I had pi over 4 here, but I don't. So I'm going to put pi over 4 there and a 4 over pi here, which these make 1, so I haven't changed anything. All right, now I'm going to get 16 over pi. That 0 and 2 got to change. Sorry about that. So this is u. That's the whole reason we did a u sub. And this is du, making it a very simple antiderivative. But these are x's, and we need these to be u's. So when x is 0, plug that in. 0 times that is 0. And then if we plug in 2, okay, that's bad. 2 times pi over 4, the 2 cancels, leaving pi over 2. So the top will be pi over 2. And then the antiderivative, I add 1 to the exponent and divide by that. I add 1 to the exponent and divide by that. That becomes 4x, 0 to 2. I'm just going to move along here. The antiderivative cos u is sine u. And then for this, I'm going to plug in 2. I'm going to plug in 2 again. And plug in 2. Then I'm going to plug in 0, but everything's going to be 0. Then I get sine. I'm going to plug in the pi over 2. I'm going to plug in the 0. Now all of this, you don't have to simplify that at all. That you can leave exactly how it is. You don't want to take a chance of making a mistake on there and losing points, so I'm going to leave that normally, but I'm just going to go ahead and simplify it just for, I don't know, so you can see how to simplify this. 2 cancel with one of those, going to be 12 plus 8. And then sine of pi over 2 is 1. Sine of 0 is 0. So it's 16 over 3 minus 4. I am going to get a common denominator. And that's going to be 12 over 3. Subtract those. And I'm going to get 16 over 3. Oh, I'm going to have to subtract them. 16 minus 12 is 4/3. So there's my answer. 16 over pi minus 4/3. Now again, you should have stopped way up here, actually with this. That should have been your stopping point. Because any mistake after that, you would lose a point. Okay, obviously this needs to be here, but that's where you should end up. So that's part A. I'm going to have to erase all this and do part B. Bear with me. I'll try to erase it without losing too much. Okay, not bad. Let me try to erase more of this. Okay, almost there. Oh, that's what I was afraid of. Didn't want to lose that box I made. Okay, part B. We don't have to evaluate, so it's nice. An integral expression that gives the volume. So we want to rotate this around this line. So we want that volume. I can already see there's going to be a hollow middle because this is the part that's going to produce this solid. If that's not there, I'm not going to have anything in the middle. I'll show you why right here. So let me do, that's not what I wanted. Try that again. Pretty good. Not perfect, but pretty good. Fill that with, I think, orange. Okay, so this is the outer edge. So this edge is going to be rotated. It's going to be small, bigger, 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 smaller, but that's the whole thing. But you can see all of this, there's nothing there. When you rotate that part, that is hollow and there's nothing. So I have to take, for part B, for that volume. Now the disks are starting at 0, ending at 2. So I'm going to have to add up all the volume of the disk from 0 to 2. And the volume is the area of the disk, which is pi r squared. And the thickness is the change in x. I need to subtract from that the hollow middle. So I'm going to do the same thing, but I'm going to have a different radius for the middle. So I have to find out the big R and the little r, R1 and R2, based on this. R1 is the bigger one. It's going to go from the farthest function to the axis of rotation. That's going to be my R1. So R1 is the big Y, which is here, which is 4, minus the little y, which is f of x. So that's going to be 4 minus f of x. So that's the whole huge bowl. Now I have to subtract this hollow part here. It's just that middle part that needs to be eliminated. So what is that going to look like? Let me erase this. Let me put this R1 on the other side. That's R1. So the small part in the middle, let me duplicate this and move it over and shrink it. So you can see the hollow here? That's the radius of the hollow. And the same thing happens. It's going to go from my axis of rotation to the closer graph. So that's going to be R2. And the big Y is going to be 4, and the small y is going to be g of x. So that's going to be my r's. And I'm pretty much done. I just plug these in for my R1 and R2. Actually, I don't even have to do that. By saying R1 and defining R1, that's implied that that is there. And saying R2 squared and defining it there, that's the same as having that there. So in essence, that is my final answer. You could plug the values in, but you have a chance of making a mistake. I think this is cleaner and much better. And I didn't give a points breakdown. I don't think I did. I don't remember. But on this particular part, I hope I did on the other one. I'd probably give you 1 point for having the integral from 0 to 2. 1 point for having R1 squared. 1 point for having R2 squared. Maybe even a point for subtraction. So that's kind of how the breakdown's going to go. I can't remember if I did it for part A. I don't think so, but hopefully with enough examples you will see how the points are going to work. All right, one more part. We have part C left. I'll do that next. Let me erase this stuff. Okay, part C. We don't need this stuff either here. So R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis, here's the x-axis, perpendicular is this way, is the base, which is a square. So my base is going to be perpendicular to the x. Call that the base. And on that, I'm building a square. So I'm going to go up out of the paper, try that again, up out of the paper and building a square. So hopefully you can see that. They're going to start here and end up here. So I'm starting at 0 and ending at 2. So for part C, the volume, I add up the volume of all the squares from 0 to 2. And the volume is the area of the square times the thickness. But the base and height of the square are the same, so it's going to be b squared, and the thickness is the change in x. So let's define b. That's just going to be g of x minus f of x. I am pretty much done because we don't have to evaluate that. I can stop here. Since I have defined b as g minus f, this is as if I have g minus f squared written there, and that's the answer. Breakdown of points, probably give you a point for knowing to integrate from 0 to 2, knowing that we have b squared, and defining b, all that together is probably going to be 1 point. So probably 2 more points on that last part there. And that's it for 2013.